Welcome back, everyone. Now, in this lesson, we're going to be talking about what we call just attributes of series. So we're going to be talking about like what a series is, what it looks like, what it does, and just kind of some background information on it. But before we get into series, I do want to do a recap of sequences. So up here in this corner, I do have the explicit forms of what we call the arithmetic sequence and a geometric sequence. So an arithmetic sequence is going to be linear in nature, whereas a geometric is going to be exponential in nature. So we're going to do a kind of a recap of these because the sequences are going to be coming back when we talk about series. So I'm actually going to do some of the warm-up here. I'm not going to do too much of it, just to kind of do a recap. So if I'm given the sequence here, I'm going from 3 to 9 to 15 to 21. I want to find a common and similar difference between all the terms. So to go from 3 to 9 to 15 to 21, I'm going to add 6. So adding 6 is going to be my common theme here, my common value. So what this tells me, because I'm adding or subtracting, this is going to be an arithmetic sequence. And then in an arithmetic sequence, we're going to have what we call a common difference. And a common difference in your sequence is going to be denoted with the letter D. And then your change that we have up here, that plus 6, this is going to be the value of your common difference. So whatever that changes, that's what your value is here. And then down here, we actually want to evaluate the 10th term. So whatever number is in the subscript of your A here, that's going to tell you the term value that you need to find. So I'm going to use the explicit form. So I want to find A sub 10, which is the 10th term, and I need to find the value of the first term, and then I'm going to do the term number minus 1 times the common difference. So when I plug in, so the first term of my sequence is going to be 3, and then plus the term number I want to find is going to be the 10th term, so 10 minus 1, and then times my common difference here. So this is going to be 3, that's a 3, plus 9 times 6, which tells me that this is going to give me, was that 57? Yes. Yes, sorry, I had to make sure. Now for the next one, over here, we're going to do 1 to 3 to 9 to 27 to 81. Now what's going to happen here is we're going to be multiplying. So to go from each term to the next, we're going to do times 3, times 3, times 3, times 3. Now because we're multiplying, that's going to make this sequence geometric. Now a geometric series, not yet. A geometric sequence is going to have what we call a common ratio, which is going to be denoted with the letter R. And then our change here, once again, we're just going to take that change. It's going to be equal to 3. So over here, I'm going to use the calculator for this one because I'm not trying to do this one by hand. So this means we're going to be using the form a sub n equals a sub 1 times your common ratio raised to the n minus 1. So when I plug in, the first term in this case is going to be 1 times 3 raised to the 10 minus 1, which means I want to find 3 raised to the 9th power. Now 3 raised to the 9th power will be 19,683. So that's kind of your little backstory with sequences, which we're going to use to kind of segue into what we call series. So with series, we're going to look at the distinct difference between them first. So a sequence is going to just describe a set of values. And then those values are going to be separated by commas, which is what we saw up here in the first couple problems. All these values are going to be separated with these commas. Now a series is going to describe a summation, which means we're going to add all these values together. And then in a summation, these values are going to be separated using operations, but specifically using addition and subtraction. Then we're also going to look at what we call an infinite or a finite series and or sequence. So between the two, what you're going to be looking for is what we call an ellipsis, which you may have seen in an English class or any type of writing. So if you see an ellipsis, that means it's going to be going forever and ever, which means it will be infinite. But if there's no ellipsis, that tells you that it's going to be what we call finite, which means it's going to stop at some point. So now looking at this table below, what we're going to do is we're going to be identifying whether the whatever we have over here on the left side, whether it's going to be finite or infinite, and then we're going to determine whether it's arithmetic or geometric, and then determine whether it's going to be a series or a sequence. So looking at this very first one, so I'm going from 1 to 5 to 9 to 13 to 17. So to go from all these terms, first off, that's going to be plus 4, which tells me right there that's going to be arithmetic. So what I'm going to do is I'm just going to duplicate and then bring it down. And then there is no ellipses at the very end, which tells me that this is going to be finite. And then, looking at the next part, we want to determine if it's going to be a sequence or a series. Well, I see commas here, which that's going to be an indication to me that it's going to be a sequence. I figured copying and pasting will be way easier and quicker than just writing it all out 20,000 times. Now for number 2, or number 5 rather. So to go from, well, let's actually start on the left side for finite or infinite. So I see that we have an ellipsis here, which tells me that this is going to be infinite. So with infinite, we're going to put that there since we have the ellipsis. Now we're going to look at if it's arithmetic or geometric. So I'm going to look to see how do I go from 2 to 4 to 8 to 16. All these values are doubling, so it's times 2. Because we're multiplying, that tells me it's going to be geometric. And now, last but not least, we want to determine if it's going to be a sequence or a series. I see addition signs here in between each of these terms, which means we're going to be adding them together. And because we're doing a summation, that tells me that this will be a series. Now, I would suggest pause here and actually fill in the rest of the table, or you can check it with a key, but I'm actually going to move on. So looking on, we're looking at what we call sigma notation. So sigma notation is using the Greek letter sigma, which is what you see here. So this symbol in mathematics just means that we're going to be finding the summation. So which is what we're going to put over here, which I forgot to write this in. So in your sigma notation, you're going to have numbers or values written below and above. Now, the values that you're going to write below are going to be what we call the lower bound. And then the value on the top is going to be what we call the upper bound. Now, this just kind of tells you where we're starting and where we're ending, which is what we have over here. So I know some people call it a lower bound or even a lower boundary, then upper bound or even upper boundary. Doesn't really matter which one you use. It's tomato, tomato, for lack of better terms. And then what we're looking at next is going to be the actual equation that's being written here. So this is going to represent some sort of function or equation that we're going to actually find the sum of. So we're going to look at that in a bit. So down here, I have the actual formulas that we're going to be referencing for series and sequences. So over here, the sequences, this should look very familiar. This is what we just did in the warm-up, which should be a recap. And then over here, we're going to have the formulas for a partial sum, which is finite, and then also an infinite sum. So with your finite for arithmetic, which means we're looking at this box right here, there's actually 2 different formulas that we can use. So we can do the number of terms divided by 2, and then multiply that times the value of the first term of the series plus the last term of the series. Now, speaking of this a sub 1 right here, because I have this written everywhere, so this is going to be the first value of the series. However, it may not necessarily be the first term. So meaning it may not be a sub 1 that you're going to plug in. So the first term of the series, it may start at the 3rd term. It may start at the 5th term. It may start at the 10th term, for example. So the sub 1 right here, I know can be a little misleading. It's not necessarily the first term. It's just where does the series start? Am I starting from the 3rd term and going to the 8th term? Am I starting from the 5th term and going to the 10th term? It just depends on what's written. So that's just a very important caveat that I need everyone to kind of take note of. And then for your partial sums, we're also going to look at our geometric. So the same idea happens here because of this a sub 1. It's the first term of the series. And then you're going to be plugging in your common ratio, number of terms in these multiple places. And then same idea up here for arithmetic with common difference. Now we're going to look at what we call an infinite sum. So your infinite sum is going to be if we're going to compute an infinite number of values and we're going to add them together. Now with arithmetic, it's either always going to be positive or negative infinity depending on what the common difference is. If your common difference in an infinite sum is positive, then it's probably going to be a positive infinity, most likely, most definitely. And then if you have a negative common difference, then that means we're looking at a sum of negative infinity. And then same idea down here for an infinite geometric. You're going to plug in the first term of the sequence, which should actually be the first term since it's infinite. And then you're going to do 1 minus your common ratio in the bottom. Now, this specifically in the bottom for the infinite sum of geometric, this is going to be if your R value, the absolute value of your R value, if it's less than 1. This is where we're really going to use this. Because if it's infinite, or rather, sorry, if the absolute value is bigger than 1, then it will actually go to infinity or even negative infinity, depending on the R value. But if it's less, then it's actually going to have some value, which means it's going to converge, which we're going to talk about convergence and divergence in a bit. So speaking of convergence and divergence, that's what we're going to look at next. So looking at the series type, we have an arithmetic and a geometric series. Now down here, I also have harmonic and p-series listed. Just FYI, this is kind of a sneak peek into when you get to AP Calculus, but more specifically AP BC Calculus. So these are just kind of a couple of the many different types of series. There's also going to be Taylor series, Maclaurin series. There's going to be all sorts of different series that we're going to be looking at when you get to BC, but for pre-cal, we're not going to look at those right now. This is just to kind of give you a heads up as to what you're looking at. So we're not going to worry about those. We're going to focus mostly on arithmetic and geometric, which is what we have here in these top two. So looking at your series notation, this is going to be your arithmetic explicit form that we're going to use for an explicit, or nope, not for explicit, for arithmetic series. There we go. Words are hard, y'all. Now, notice how this is an explicit form of an arithmetic sequence. Now, what we're going to do is you're actually going to end up converting this to slope-intercept form. So y equals mx plus b. And we're going to get to some problems like this in a little bit. Then for your geometric series, now over here, we don't really have a conversion, but I do want to show you some conversions later. That's going to happen when we get to dealing with the n-1 and the exponent. So I will let you kind of look at these, and then we're going to kind of look on at a few other things. So here is a note down here about convergence and divergence that I'll let you kind of read. Long story short, we're going to essentially treat an infinite sum kind of like a limit. And then if that limit can be found and if it exists, that means it's going to converge. However, if that limit doesn't exist or if it goes to positive or negative infinity, then that means it's going to diverge. So I almost like to think of it as exponential growth and decay. If it's going to go towards a positive or a negative infinity, to me, that's going to tell me it's going to diverge. However, if the value as the limit goes on to infinity, if it actually approaches some value, to me, that's what's going to make it converge. So that's how I like to think of it. So looking at these problems down here, what we're going to do is we're going to write the following in sigma notation. So starting off, I'm looking to see, first off, if it's going to be arithmetic or geometric so I know which explicit form to actually use. So if I'm looking at my terms and I go from 3 to 8, 8 to 13, and then to 18, I can see my change here is going to be plus 5. So because we're looking at a change of plus 5, that means we have a common difference, which means we're going to be looking at an arithmetic series. And then because of the ellipsis over here, that also tells me it's going to be infinite. So what I'm going to start with is writing my sigma. And then on the bottom, I'm going to say n equals 1. We're going to start at the first term. And then it's going to go on indefinitely, which means I'm going to write an infinity on the top. Now the next part is I'm going to write my series in terms of the arithmetic explicit form. So I'm going to write it in terms of a sub 1 plus n minus 1 times the common difference. So this is going to turn into n equals 1 going to infinity. So I'm going to plug in for the first term, which is going to be 3, and then plus the term number, which we're going to leave as n, since that's what we're evaluating, and then you're going to write in your common difference, which we know is 5. So now that we have it written in terms of the arithmetic explicit form, now I want to rewrite it in terms of slope-intercept form. So you're going to distribute the 5. Sometimes writing that sigma takes a little bit of practice. So this would be 3 plus 5n minus 5. And then when you rewrite, I'll just write it up here. So we're going to have 5n minus 2. So this would be writing it in sigma notation. So notice how I did put parentheses around the entire argument here. You have to put parentheses if it's more than one term, because I will say, I'm going to write this incorrectly on purpose so you can see what I'm saying. If I didn't have those parentheses, then what this is saying is I'm just going to find the series in the summation of just that first value, and then find that series, and then I'm going to subtract 2. So those parentheses are telling you that the -2 is included in that argument. So you've got to watch out and make sure you're including these parentheses when you need them. So now looking at the second one. So same idea, I'm looking from 15 to 11 to 7 to 3 to -1 to -5. So my common difference here is I'm subtracting 4. You don't have to write it for every single one. I just like to out of habit. So once again, I'm going to go ahead and start with my sigma. Now, we don't have an ellipsis at the very end, which tells me this is going to be finite. So I'm still going to start at the first term, but we don't know what number we're going to put up here. Well, whenever we give you a finite series like this, you just count the number of terms. So we have 1, 2, 3, 4, 5, 6 terms here. So that 6 is what I'm going to write on the top. So now I need to actually write my explicit form equation. So I'm going to start with a sub 1, which is 15, plus n minus 1 times my common difference, which is going to be -4. Now, another very important note, make sure you're writing that negative here in parentheses, because if I don't write the parentheses, it looks like I'm subtracting 4 instead of multiplying it times a -4. So that notation is very, very, very important. So now we're going to convert, so I'm going to distribute this -4. So we're going to have sigma going from, or the series summation from 1 for the first term to the sixth term. And then it's going to be 15 minus 4n plus 4. So then that means my sigma notation from the first term to the sixth term will be -4n plus 19. So this would be my sigma notation. Now moving on, now looking at 13. So if I go from 4 to 12 to 36 to 108, well, my change here is actually going to be times 3. So this tells me we're looking at geometric. And then also notice there's no ellipsis at the very end, which means this is going to be a finite. So we have 1, 2, 3, we have 4 terms. So I'm going to go ahead and start my sigma notation. So we're going to have n equals 1, and then to 4 terms. Now for your geometric explicit form, I'll write this up here just to kind of go ahead and give you a heads up. So the first term, which is a sub 1, times r, which is your common ratio, raised to the n minus 1. So I'm going to do 4 times 3 raised to the n minus 1. So this technically is your, what's it called? Your sigma notation for this one. However, there is kind of some extra steps that we could technically follow, and this is that caveat I mentioned earlier. So I'm going to go ahead and actually continue this one. And then what I'm going to do is manipulate this 3 raised to the n minus 1. I'm going to actually separate it. So I'm going to rewrite it as 3 raised to the n times 3 raised to a -1. And then what's going to happen here is I can rewrite this as sigma from the first term to the fourth term, or the summation rather, And then this is going to be 4 times 3 raised to the n, and then that negative exponent over here, 3 raised to a negative 1, I'm going to change this to a 1/3. And then I can multiply the 4 and the 1/3 together, which means I'm actually going to get summation from the first term to the fourth term of 4/3 times 3 raised to the n. So this is just another way of writing the summation. It's also equivalent. If it's multiple choice, whatever, we could technically ask for either one of those forms. So now I want to give you guys a few minutes. I want you guys to try 14, 15, and 16 on your own. And actually, I'll probably just do 2 of these. And we'll see. Maybe I'll do all of them. Who knows? So let's look at 14. So I'm going from 100 to 97 to 94 to 91. So let's see. These actually should be plus signs. That is a typo. That is my bad. I will make sure I fix that later. Okay, so what I see here is we are subtracting 3. Nope. And then I also see that it's infinite, so we have an infinite arithmetic. So I'm going to go ahead and start with my sigma. So this is going to be n equals 1 going to infinity. And then we're going to start with the first term, which is 100, plus n minus 1 times your common difference, which is negative 3. So I'm going to go ahead and distribute. So we're going to have n equals 1 going to 100, not 100 to infinity, and then 100 plus, actually rather, minus 3n plus 3 when you distribute that negative 3, which means my series in sigma notation will be the first term to infinity, and then negative 3n plus 103. Ta-da! Okay, so 15. So looking at this one, so I'm going from 256 to negative 128 to positive 64 to negative 32. So the important part here, hopefully that's obvious, is notice how we are alternating signs. So the first value is positive, so we go from positive to negative to positive to negative to positive, so we have an alternating sign. Whenever you have an alternating sign like this, what that tells you is you're going to multiply by a negative. So to go from 256 to negative 128, we're going to multiply by a negative 1/2. So that tells me we're looking at an infinite geometric. So I'm going to do my sigma, so n equals 1, going to infinity. Then the first term, which is going to be 256, then parentheses negative 100, not 100, hello, 256 times negative 1/2 raised to the n minus 1. So if we want you to just stop there, you could just stop there. However, I'm going to go ahead and keep rewriting just in case. So this would be n equals 1 going to infinity of 256 parentheses negative 1/2 raised to the n, then negative 1/2 raised to a negative 1. So this is going to turn into n equals 1 going to infinity of 256 negative 1/2 raised to the n, and that negative exponent tells me I'm going to switch the fraction, so I'm going to flip it, so it's going to become negative 2. So then when I multiply, I'm going to have the first term of 1 going to infinity, and then negative 2 times 256 is going to be negative 512. And then multiply that times negative 1/2 raised to the n. So either one of these would be acceptable. So 16 is going to follow number 15 very closely. The only difference here is that you're, once again, we're alternating signs, but the value is staying the same. So you're just going to multiply by negative 1. That's really the only other difference I wanted to point out. So now that we wrote these values using sigma notation, now we're actually going to evaluate these sums. Now, I'm going to do this kind of the long way just because I want you guys to kind of understand what it means to do a series. So looking at this first one, I want to go from the first term to the fifth term. and I want to use 3n minus 5 to actually evaluate what this sum's going to be. So what I'm going to do is, well, there's multiple ways you could do this. So this is telling me I want to do the first term plus the second term plus the third term plus the fourth term plus the fifth term. So if you look, if I count the number of terms, we have 1, 2, 3, 4, 5 terms. So over here, I'm going to put a 5. Now we actually want to find the summation. So there's a bunch of different ways and layouts that you could do. For these, sometimes I just like making a table. So I'll just make a table for these actually. So I'm going to do n and then a sub n for my sequence. So I know I want to find 1, 2, 3, 4, and 5. So if I plug in 1, that's going to be 3 minus 5, which is negative 2. 2 times 3, which is 6, minus 5 is 1. So then I'm just going to add 3, which means 4, 7, and 10. So I want to add all these values together, which means I'm going to do negative 2 plus 1 plus 4 plus 7 plus 10. And then this is the sum that I want to evaluate. So I like to do this kind of one at a time just to make sure I don't make any dumb mistakes. So this is just going to be negative 1 plus 11, which is going to be 10 plus 10, which means our sum here is going to be 20. So moving on. Now with 18, so we want to start at the second term, and then we're going to go to the fifth term. So this means that I want to start at a sub 2, and then add a sub 3, then a sub 4, and then a sub 5. Now notice how we're we're ending at the fifth term, but we don't have 5 terms. We're actually only going to do 4 terms. So the number of terms here is just going to be 4. But what you want to notice is if I want to actually find a consistent way to find the number of terms, what I like to do is n is going to equal the top number minus the bottom number, and then plus 1. So the number of terms is going to be 5 minus 2 plus 1, which is 4. So this is kind of your quick, easy way to find the number of terms that you're going to have. So same idea. I'm going to go ahead and just make a quick little reference table. So we're going to start with n and then go to a sub n so we can find the term value. So I'm going to start with 2, then 3, 4, and then go to 5. And then I want to go and find the actual term value, which is a sub n. So if I plug in 2, it's going to be 2 squared, which is 4. 4 times 2 is 8, plus 1 is 9. 3 squared is 9, times 2 is 18, plus 1 is 19. 4 squared, 16, times 2, 32, plus 1, 33. Then 5 squared, 25, times 2, 50, plus 1, 51. So this means we're going to do 9 plus 19 plus 33 plus 51. So that's 28 and 84. Just going to be, what is that, 112? I hope. I can't do math. Everything's fine. Yes. Ta-da! Sorry, it's still early for me. I didn't have my coffee today, so I am going to double check all my math, even if it's basic math. Now, number 19 down here. So same idea. We're still going to be evaluating a partial series, or a finite series, rather, not really partial. Partial is another way that you could really say it, I guess. So we're looking at a geometric series now. So I want to find from 1 to 6. So I'm going to do a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 plus a sub 5 plus a sub 6. So we're going to have 6 total terms. And then we want to find the summation. Now, these numbers are going to get kind of ugly. So for this problem, I actually want to practice kind of the calculator skills. So I actually typed up the steps down here for you. That way you could use your calculator if you do get kind of a gross series. Let's run through this real quick. So with your steps on the Casio, you're going to press menu, then go to run matrix, and then we're going to press F4, which is going to be your math symbol, and then you're going to press F6 to toggle over to the next screen, and then you're going to see the sigma under the button F2. So when you type that, then this is what's going to pop up on your screen. If I could zoom in, that would be great. So when you get here, or when you get this entry, what's going to happen is it's going to ask you essentially, what variable do you want to use? What's the value of the first, or what's the first term you want to start at? What's the upper bound? And then you're going to type in your equation. So for this one, if I reference, let me actually do this. I only need this little part. Let's see if I can. There we go. So I'm going to go ahead and write it here. That way you know exactly what to type in on your calculator and what it should look like. So when you get here, what you're going to do is you're going to type in your variable x, and then that's going to equal just 1. And then we're going to go up to 6 terms. And then you're going to type in your actual equation in this blank here. So in that blank, you're going to have parentheses, which are already going to be here. And then you're going to have 10 parentheses, 1/2, and then raised to the x minus 1. So because you're defining the x value, you have to match whatever value or whatever variable you're plugging in. Now, of course, these are also going to be in those outer parentheses that are in blue. So let me go ahead and type that in. So if you haven't already, I would actually practice. This is a good time to practice using the calculator for these. So when I plugged it in, I get a summation of 315 over 16. So some of your numbers may not be very pretty, but that's okay. That's totally normal. So 315 over 16. That's not a 6 or a 1. Everything's fine. I really need some coffee. All right, now we're going to move on. So this is kind of the last section. So now we're going to determine whether the series is going to converge or diverge, and then we're going to justify why. So we're going to kind of recap what we talked about up here, which I know was kind of brief. But with an arithmetic series, if it's finite, it's going to converge. Only if it is finite will it converge. But if it's infinite, it's going to diverge. So all of these values here are under the assumption that we are infinite. So that's why you see the never here. So if it's infinite, it's never going to converge. It will always diverge. But if it's finite, it will converge. Now with geometric, if it's finite, it will always converge. So finite series will always converge because we can actually find the value. But if it's infinite, then we are going to abide by these rules here. So if your common ratio is less than 1, the absolute value of it rather, then that means it's going to converge, which means we can actually find the specific sum. But if the common ratio is bigger than 1, the absolute value of it, that means it's going to diverge and it's going to approach negative or positive infinity. So looking here, so I have infinite, and we want to determine arithmetic or geometric. So we're going from 1 to 5 to 9. So this change is plus 4. So it's infinite arithmetic. And infinite arithmetic always diverges. Now looking at 21, so I'm going from 100 to 25 to 25 fourths. Now this is times 1/4. And it is infinite, so infinite geometric. However, my R value is equal to 1/4, which in turn, that is less than 1. So because the ratio is less than 1, that tells me it's going to converge. So whenever it's going to converge, that means I can actually evaluate and I can actually find what that infinite sum is going to be. And that infinite sum can be calculated using this formula right here, which we're going to get into actually finding these sums in the next lesson. So now I have 22, so we're going to have 1/9 plus 1/3 plus 1 plus 3. It's infinite, and I want to look to see what my change is. So to go from each of these terms, I'm multiplying by 3. So because I'm infinite geometric, my R value is equal to 3, which in turn, that value is bigger than 1, which means it's going to diverge. So now looking here, so I see I have 1 plus 5 plus 9 plus 13 plus 17 plus 21. I also notice there's no ellipsis at the end, so automatically this is a finite arithmetic, which means we're going to converge. So you essentially want to ask yourself, can I find the sum? If I can find the sum and it's not infinity, most likely it's going to converge. This chair is really squeaky, y'all. I don't know what's going on. Okay, now looking at 24. So I'm going from 3 to -6 to +12 to -24 to +48. So my value here, I'm going to multiply by a -2. I'm not going to write all the -2's. So the absolute value of my R value, it is 2. Now, I know that that value is bigger than 1, which tells me that this is going to diverge. And then over here, so with 25, we're going from 625 to 500 to 400. Now, sometimes your common ratio or your common difference or whatever, it may not be very obvious. So I'm going to try a common difference first. So to subtract, I would actually have to take away 125. But that won't work here because that would just be minus 100. So I can't do an arithmetic sequence here. So that tells me it has to be geometric. So for geometric, that means I need to find out what I'm multiplying by. So to find it, what I like to do is I like to do the value of the second term over the value of the first term. So 500 over 625, and then I simplify whatever this value is. So I can simplify by a value of something bigger, probably, was that 125 I think I can do? Yeah. Which would give me 4/5. So that means I'm multiplying by 4/5. The absolute value is still 4/5. That value is less than 1, which means here we would converge. So I can actually find that infinite sum. So, ta-da! Hopefully this was insightful. Hopefully you had a great time. Make good choices.